Engineering 305, example problem 5.14. Let's get after it. The machine part shown in figure 522 is 20 millimeters thick and is made of 0.4% carbon hot rolled steel. Determine the maximum safe load P if the maximum normal stress is not to exceed 144 megapascals. I find that interesting in the problem statement that they're telling us the material and then they don't make us go look it up. They should have us flip into the front cover of the book but whatever. Actually, if we're doing the problem in metric, that would be the back cover. But the safe stress, so I'll start taking some notes here. The safe stress, and I'm going to call that sigma allowable. And you'll see that for me a lot, sigma A. And I use that because it's not necessarily the yield, it's not necessarily the ultimate, it's just what I'm going to let go in this situation. That's what I believe is safe, that's what's allowable. So sigma allowable is 144 megapascals. And then next step, well, what's my equation that I'm working with? Well, that's equal to, it's over here on the corner of the page next to my picture, K times P over A. So now, really, if I want to know what P is, I just have to reorganize my equation to sigma area divided by K. And now I can start putting stuff in. P is equal to 144 megapascals times an area. Well, so I need to know the area. And actually, that's a nice problem to have. And then I need to know my stress concentration factor. Well, okay, maybe I should have gone through this a little bit better. There are two areas where the stress is heightened. There's this area here, and that corresponds to this red chart. And then there's this area here where this necks down, which is this other chart. Now, if you watch the lecture, you said, I don't know whether this piece is, whether this green chart, chart C, is for something that's axisymmetric or something that's a flat slab. And I thought it was axisymmetric, but now we're going to do this problem and we're going to do it with a flat slab. So it must be that it's for a flat slab. And I should probably go find a chart for an axisymmetric neck down with an axial load. I know I have it in the office, it's just a matter of tracking it down. So if I start by solving the red problem, which is this, and what I mean by the red problem is I've got to find my maximum load through that where I've got the hole, then P is equal to sigma 144 MPa. And now I'm back to, I need to know what my area is. And there's two different areas I could use. I know that I could either use, well, it's the thickness. I know it's the thickness times the width, right? But is my thickness the 90 millimeter, or sorry, is my width the 90 millimeters here? Or is it 90 minus the diameter of the hole? Because either I can think about it, let me clear up some of this stuff on here. I can either think about that as this area, or I can think about it as that whole area all the way across that then goes back into the page. And we've got to decide that, which one of these that it is. Is it that or is it the other? And to do that, I brought this part of the textbook in for us. Well, I wanted to just flare that up. There we go. This probably should have been covered in the lecture, but I didn't do it, and so we get to cover it now. So the expression for the maximum normal stress becomes, and they give us that equation, where A, the area, is either the gross area or the net area. Now, it can't be both. It can't be both. What they're going to tell us is now starts the net area. It defines it, the net area, which is the area at the reduced section. So you get these curves that are similar to the one shown in 520. You can find them in all kinds of handbooks. And you need to know which one you're using, whether they're based on the gross or the net. So the factors that they're showing us, KT, are based on the net section. So if we go back up here, let me shrink this. Or I just push it out of the way and spin it a little bit. If we go back up here to these figures, you'll see that these are all calling this out in terms of KT. Oh, KT right there. So that means I use the net section. So I'm going to go slide back over here, and I'm going to go, my thickness was 20 millimeters. And my width is going to be the 90 minus 27. Now, I still don't know what K is. To get K, I need to go to this chart. That 90 minus 27, oh, you know, I should put the units on that. 27, and, well, that's millimeters. I'm going to put it outside. So that is going to be 63 millimeters. That's my little, and that's important because as I'm looking for this stress concentration factor, this figure 2, I need to know the diameter of the hole over the width. Oh, okay, diameter of the hole. Well, for us, the diameter is 27 and the width is 90, so that's about 0.3. So this is 0.1, 0.2, 0.3, 0.4, 0.5, so I'm going to say 0.3. It's about here. It's about here. It's about there. So this is 2.2, 0.4, 0.6, 0.83. So that's about stress concentration 2.3. All right. Back over here, 2.3. And now I just have to do the math. I can get out my trusty dusty calculator, or I can spin ahead, and I am going to get P is equal to 78.9 kilonewtons. Again, my meters here are going to cancel with the pascals as a newton per meter squared. These are millimeters. That's why I dropped from mega to kilo. But there's my answer. That's for, I'll say for part 1. The hole at the hole. I'm not done yet. I'm not done because I also have this green stress riser. So really that sets up a second hole problem, which looks exactly the same. P is equal to sigma area over K, which now this is still 144 megapascals. Now my area is going to be the net area, and so that net, I'm going to use the 60, not the bigger area, but the smaller. So it's 60 millimeters times the 20 millimeters. And now I need a new K factor. So let's go back. We'll blow this chart up. I need a new K. So my radius over my small diameter. Oh, I don't remember that. My radius is 15. So my small diameter. Sorry, D, small d. I don't know that that's a diameter. It can't be a diameter. Or maybe that works for both. Maybe the stress concentrations work the same way, whether it's radial or whether it's a bar, flat bar. I can't believe that they do, but we're going to run with it. So my R over D is 0.25 because R, it's equal to 15 over 60. And so that's 0.25. So that's going to put me on this point there. And then D over D, my big diameter was 90, and the smaller one is 60. So that is going to be 90 over 60, which is equal to 1.5. So now I got to pick the right line, which is this one. That's 1.25. So I'm on this second line, and it's going to be right there. So this is 1.2, 0.4, 0.6, 0.8. So this is 0.2 per division. So that's 1 point. It's above the 1.6. It's not to 1.7. You know what? I could pick a 1.65. That would be a good guess. I could also pick K equal to 1.7 because I know it's not that big, but that gives me a more conservative answer. So I'm going to go with 1.7. I know it's not that high. And then if I calculate that out, oh, hold on, let me grab the calculator again. So then I get, I got 101,647, and that's just 102 kilonewtons. 3 sig fig, really? You can't. And look at it. We can't even agree on, or we could agree, but that number 1.6 could have gone from, or I use 1.7, could go from 1.6 to 1.7. I know it's above 1.6, but it could have been anything in there. Would have been a reasonable guess. So I'm only accurate in that to 2 significant figures, not even to 3. And so to go beyond 3 significant figures, which I tell you that because I asked for 4 significant figures on the test, and many people on Friday, and many people would put 4 decimal points behind the 4 digits behind the decimal point when I was looking for the leading 4 digits, nothing beyond the decimal point. But that's okay. Anyway, some interesting lessons to take away from this. One, I really think is sig figures, the number of significant figures. I think for these problems, we really have only 2. We cannot get that stress concentration factor out of those charts beyond 2 significant digits. So that's the first thing I want to note. Yeah, maybe that's it. I mean, oh, and then no, the net area versus gross area. Net versus gross, and this is the small, and this is the large. And if you wanted to go, if you want to use the other one, they do have an equation here to convert them back and forth. So you can look at that. We are going to have stress concentration factors for every type of load. So that's something that you should not challenging, but you should get comfortable picking the number out of a chart. There isn't a theoretical explanation. There is a theoretical explanation, but there's not a theoretical equation that we can just apply and say, here's your answer, here's your sign. This is what we get, is we get these lookup charts to provide a correction factor, and we go with that. So that's what I got. Hope you're doing well. More to come.